Okay, so I think we'll get started then, as we're just coming up to the hour. So today we've got our very own Alexander Dittmann, who is an Einstein Fellow here, coming all the way from his office upstairs in the IAS. But you previously completed your PhD under the supervision of Cole Miller at Maryland, where you also spent some stints as well at Los Alamos and the CCA, working on a variety of topics. We've heard about some of them at Astro Coffee. I went onto your website just to list off all your various publications, but they're covering things like numerical methods, stellar evolution, pulsar characterization, variety of accretion disk physics, and other astrophysical fluid dynamic problems. And today we will be hearing all about accreting binaries. So take it away, Alex.
Well, so thank you very much for that introduction. I'm happy to have this chance to share some more of my research with all of you. This intimated it's a little difficult to cram everything into one talk, so I'm glad to have this opportunity to talk about binaries. So this is work that I conducted during my time in graduate school, primarily actually with a postdoc formerly at Maryland, Cole Miller, who's now a scientist at the Perimeter Institute. Also a little bit of work with my advisor, Cole Miller. And also I spent a couple summers at Los Alamos National Lab working with Adam Dempsey and Greeley. Now, to begin with, I'm going to give a brief overview of circumbinary disks generally. So they're, how they might form, their structure, how binaries can evolve due to interactions with these disks. And after that, I'll move into a few specific cases. So looking at the evolution of supermassive binary black holes, specifically as they enter the Lisa band, as gravitational waves start to become dynamically important for their evolution. And after that, I'll talk a bit about black hole binaries and AGN disks, which hopefully most of us remember from Donnelly's colloquium earlier this semester. To begin with, I like to start here. Hopefully this is familiar to most of us, depending on the route you take to the dining hall or coffee. This should be intimately familiar. In addition to all of this beautiful gas and these stars, I like to think about galaxy mergers because galaxies tend to bring with them supermassive black holes in their centers. So after these galaxies merge, they can go and give us black hole binaries to try and observe. Additionally, these galaxies are filled with other binaries. So really it's binaries all the way down. So actually most of these stars, at least the more massive ones, are actually in binary or triple or even quadruple systems. So an observation of this sort of thing is shown here. So this is a collection of a huge number of various observations looking at stellar multiplicity. So if you have a star of a given mass, on average, how many companions does it have? So on average, a solar mass star will have maybe half a companion. But if you go up to 10, 20, or 30 solar masses, then the average star is in at least a binary, if not a triple or quadruple system. And we can understand a little bit of this theoretically from looking at the collapse of giant molecular clouds into stars. So as these clouds collapse, they can fragment and form a bunch of different stars. So here we have all these little dots or various stars. There's still some gas left over that can form accretion disks around them. Here is just one triple system that kind of resembles that almond image I showed earlier. And one thing we would like to understand is how this gas that is left over from the formation of these stars affects the properties, orbital, and masses of the binaries we observe today. There's a couple examples of this are the mass ratio distribution of binaries and also the eccentricity distribution. So this top row is showing an overabundance of binaries of very nearly equal mass. So actually just to define notation a little bit, so I am a barbarian and I define the mass ratio to be the secondary mass over the primary mass. And so there's an overabundance of mass ratio 1 binaries. And this can be understood, well, possibly as the result of some circumbinary interactions I'll discuss later. This was known for a while, but with this study using Gaia, they identified a population of this out to, well, very large separations in excess of tens of thousands of AU. There are also, from observations of post-asymptotic giant branch stellar binaries, there's some evidence that the eccentricity distribution of these stars may be bimodal. And one thing about these observations is that most of these stars, if not all, have an infrared excess that is typically assumed to be part of a circumbinary disk. So
what would you call equal mass?
Equal mass?
Yeah, Q of what?
Q of 1 is equal mass.
Yeah, but it's never exactly 1. So what would you count as equal mass?
In this case, it's within maybe about 0.05, 0.15, something like that.
Wide, what do you mean by wide?
So in this case, wide is tens of thousands of AU. So these are two different mass bins, if you can make out the labels. This is actually part of a very large collection of observations. I just took the closest separations and the furthest separations. So this top bin is about 50 to 350 AU binary semi-major axes, and the bottom row is from 15,000 to 50,000 AU.
So the bottom panel is about eccentricities, but if you actually take,
Oh, sorry, this one is also mass ratios.
yeah, but if you also take equal mass wide stellar binaries, in precisely those definitions, they'll also turn out all to be extremely eccentric. Not like a distribution from 0 to something, they're all above 0.95. We have no idea why.
Yeah, 0.95, well, I don't think anyone has a good explanation for that. So some early studies thought that resonances would pump binary eccentricities up towards unity, but more recent hydro simulations have found evidence for either 1 or 2 modes, neither of which is at 1. So most studies now are finding that near unity eccentricities get damped towards maybe 0.4. But that's still an active area of research. That's one button. So generally, right, if we want to think about these systems, there aren't too many ingredients we can play with depending on how you count. Right, there's 2 or 3, we have a binary and a disk. And to first order, the main physical property of these systems that dictates their morphology is their mass ratio. So if this Q is near 0, then we have an accretion disk. It looks very similar to that around just a single object, maybe perturbed by a secondary that can excite spiral density waves, that sort of thing. But then as the mass ratio of the secondary gets larger and larger, its gravitational interaction with the disk will get stronger and stronger. And eventually, in the equal mass case, this gravitational interaction just rips open this large cavity that's typically 2 to 3 times in symmetric axis the size of the binary itself, typically quite eccentric. Now, even though these gravitational interactions are very strong, the binary is still able to accrete. You can see that every time one of these binary components approaches the pericenter of this eccentric circumbinary disk cavity, it strips off some material. And some of that material gets captured by the binary, forming these miniature accretion disks around it, and other material gets flung across this cavity, receiving this big gravitational impulse from the binary, shocking against the other side.
That's what drives the asymmetry of this cavity.
Hmm?
This is what drives the asymmetry of this cavity.
So that I don't think is completely fully understood. So shocks are definitely invoked to be one of the main things that makes this cavity asymmetric. Although if you have an equal mass binary, right, this is made an eccentric cavity, and the shocks should be symmetric and n equals 2. So there may be some interesting resonance interactions or something else going on to break the symmetry. If you have a, say, unequal mass binary, something with Q less than 1, or an eccentric binary, then there are more ways you can get this sort of asymmetry. That happens even for equal mass circular binaries. And yeah, so this is a plot of the surface density. I've played some funny games here where the scale is linear up to sort of the average level of the disk, and then I switched to a log scale to make it a little more visible. This sort of ridge here is actually about 2 orders of magnitude more dense than the purple. And this dark stuff is actually about 4 or 5 orders of magnitude less dense, but it's surface density. Probably. I like this because it shows the accretion streams in a sensible way. Now, one of the first questions people started asking as soon as they could actually do these simulations that were advanced enough to see accretion onto the binary is which one accretes more. So if you have unequal mass, does one or the other get the majority of that accretion from the disk? And in the early years, there's actually a bit of disagreement between the different simulation communities over which member of the binary should accrete more. So most of these early smooth particle hydrodynamic simulations found that the secondary object, the less massive one, would get more of that accretion and less would pass on to the primary. And you know, maybe this actually sort of makes plenty of sense, because if you have this cavity that's opened up, the secondary, right, from the center of mass of the system will be much closer to that accretion disk. It will gravitationally interact with a lot of that material first and potentially capture it. But then many of these early grid-based simulations found that actually the primary, the more massive one, accretes more. And there was a bit of a back and forth on it.
Solving the same equations with the same initial conditions, or
Slightly different, they would do slightly different initial conditions, and the fundamental equations were the same.
Is this horribly sensitive to the initial condition?
We'll get back to that. This bit probably not, but other parts, yes. They went about solving those equations. So that the basic assumption is to have just say mass conservation, momentum conservation, maybe something for energy with Coulomb terms, and then some viscosity. And then the way grid-based codes and particle codes approximate, say, pressure interactions or viscous interactions can be a little different. And they've converged a little bit more in recent years, but that's when there are numerical differences in approximating the underlying equations. And it turns out that a lot of this difference comes down actually to something else entirely, so gas thermodynamics. So the study, Young in 2015, looked at the previous simulations, and most of the grid-based codes had looked at relatively thick disks, whereas the particle codes had been looking at relatively thin disks. So when I say that, I mean the scale height of the disk over R, and I can also relate this to another term I'll bring up later called the Mach number, which will be the typical azimuthal velocity over the sound speed, which I will typically pick to make this equal to the aspect ratio of the disk -1. Okay, so thin disks have this much less than 1, and then thicker disks have that closer to 1. And many of the hydro simulations using grid codes had actually had H of maybe 0.5 or 0.25 R, whereas the SPH simulations had looked at thinner disks with lower sound speeds. And so this paper sort of carefully looked at the flow of mass just through the area around the binary and found that when you have a thinner disk, once matter approached the secondary, so this is the equipotential contour going through the first Lagrange point, and looking at the mass flux through that contour. And in a thinner disk, once matter enters this region of influence of the secondary, it's stuck there forever. It flows in, but it doesn't flow out. It just accretes onto the secondary. But then if you go to a hotter, thicker disk, similar to what the grid-based codes had simulated, pressure forces are more significant. There's more to this picture than just gravity. And matter can actually flow out of this contour and actually into the contour for the primary. So as you go to thicker disks, this can help the primary actually accrete more. And it turns out this is also a similar effect happens if you change the viscosity. So this actually led to a lot of disagreements between different codes. So we have some power law for the effective viscosity in these simulations. And depending on this power law exponent, if it's 0 or 1/2, you get the difference between these blue triangles and these orange stars, basically, is sort of with the same normalization, basically. So just this little thing like the precise functional form of the viscosity actually also really affects how much matter passes through to the primary from the disk around the secondary. And then, of course, the mass ratio also determines a lot of these dynamics. So if we go to the equal mass limit, then by symmetry, they should accrete the same amount on average. And if you go to a mass ratio of 0, then the primary should accrete everything. But in between, there's this non-monotonic behavior where around a mass ratio of 0.1 or 0.2, the secondary tends to accrete a bunch, 3 or 9 times more, something like that.
This number is always above 1 in this plot.
In this plot, yes. So here, I left this off. These are for Mach 10 disks, H over R of 0.1. So in this case, the secondary accretes preferentially in just about all cases. This is thin enough to be in this top regime, more or less. Yeah, and now, of course, we've opened up Pandora's box, right? We're varying other parameters besides just the mass ratio. And a really interesting numerical experiment was run circa 2016 or so, where they compared a few different accretion disks, right? Or really the same accretion disk around binaries versus single objects. So here, they basically took this disk with some thickness and then put either a single object in the middle or a binary with the same mass. And then they simulated it and measured the accretion rate off the binary and found that accretion off the binary was actually suppressed relative to the single object case. So here, this C they plot is just equal to binary m dot over the single object dot. So this is like a suppression factor when you introduce a binary. And so these thicker disks are all well and good maybe for binary stars, but if you're trying to think about binary supermassive black holes, all these classic accretion disk models, all of Shapiro-Sinyaev, predict razor-thin disks on the order of maybe H over R of 100, 1,000, something like that, apart from maybe the inner regions or with very high accretion rates. So the implication here is that if you go and approach this H over R of, say, 100th or 1,000th limit, then binary AGN might not actually accrete much at all, right? And so when they were analyzing these simulations, they found this is largely due to just less matter being captured by the binary at each pericenter passage. So as you get a colder and colder disk, less material is able to enter the neighborhood around the binary and more of it gets flung away.
Well, what is that?
That, I don't know, it's complicated and nonlinear. It's something we certainly see in the simulations, actually. Also, I'll continue along this path for a little while and show some examples.
But won't you expect the opposite? Because in the hotter disks, the pressure is more, or thicker disks, the pressure is more, so it's going to sort of, oppose the capture of material in binary.
Well, so in this case, actually, so I'll go back to this. Here, when you have this cavity, the pressure gradient is actually pointing towards the binary. So that simple argument might actually help you. And when you go to colder and colder disks, it maybe approaches more and more to the point mass limit, where you might have to rely on things like maybe chaotic instability as you at certain mass ratios with point mass orbits. It's messier. But this is actually intimately connected to the orbital evolution of these binaries as well. So it turns out for these near equal mass systems, most of the gravitational interaction between the binary and the disk happens with these streams. So as material is being either captured or flung away from the binary. And for these near equal mass systems, this is actually the dominant effect in their orbital evolution. So this material in the disk has a lot of angular momentum that is captured by the binary. It'll bring that angular momentum with it. On the other hand, this material that gets flung away from the binary, right, receives this gravitational impulse from the binary and carries off a bunch of energy and angular momentum. So the balance between this accretion or just material being flung away actually sets the orbital evolution of the binary as well, and is unfortunately very sensitive to things like the disk thermodynamics and the viscosity we assume in the disk. So here I'm showing a couple examples of different viscosities for these simulations and different Mach numbers. And so a different thing that was a bit of a saga in the community was whether Mach 10 disks should lead to inspirals or outspirals. But now, we've done some code comparisons. Everyone agrees that at Mach 10, the binary outspirals. So here, this color is the rate of change of the binary semi-major axis normalized to the rate of change of the binary mass. It's like a power law in the semi-major axis as a function of mass. And so dark green means very, very fast inspirals. These orangish colors are outspirals, which never get particularly fast. And as we just pick most viscosities and go up in Mach number, so to thinner and thinner disks, the binary inspirals faster and faster. The gravitational torque on the binary is more and more negative. This is actually more extreme for lower viscosity disks than for higher. If we go to a disk with high enough viscosity, those effects dominate this pressure contribution, and we end up getting outspirals even for pretty thin disks.
And this is for some given initial condition setup.
Yes, and actually this connects to the question they were looking at before. So they didn't realize the connection at the time, but this is very much related to the suppression or enhancement of accretion, right? So typically, if you look at the hydro equations, you have, so continuity gives you an m dot, angular momentum conservation gives you some angular momentum current through the disk. And so the disk structure is actually set by these free parameters. So you have the surface density is going to go like something that depends on your viscosity profile. Then there's some factor that depends on this ratio of the angular momentum current to the mass current, and then just some factors to give you the right units. And then there's a factor of R0 for radius. That's the other one. Right. So if you have, so if you have a disk that looks like this, or say a zero torque, and then you have something that looks like this for a steady state condition, or say a positive angular momentum current, and you have steady state that looks something like this for a negative angular momentum current.
What is the implied bit?
So this is, yes, I will put that shortly. So this is like sigma. This is like the surface density of the disk. So for just different angular momentum currents through it for a particular viscosity profile. So if you initialize your simulation assuming zero angular momentum current, like you would for a tiny little point mass in the middle, and then binary basically sets this boundary condition on the disk for some other angular momentum current, the disk will need to adjust, and that can take some time. So actually many early simulations of Mach 10 disks where the binary outspirals, right? So they have this positive angular momentum current. So they actually found enhancement of the accretion rate. And then these other simulations didn't connect it to orbital evolution at the time. But when you initialize a disk with zero and then the binary inspirals or experiences a negative torque, you get this suppression in the accretion rate as the disk tries to adjust from one profile to the other. And
I know one has to go one step at a time, right? But
yeah,
these are not how binaries are actually formed. It
No,
needs to be
absolutely. So it's-
environments. So
yeah, so this is very sensitive to the initial condition. And I think going forward, that's going to be an interesting thing for people to look into is if you have a realistic accretion flow forming a disk around a binary, what happens? And one reason I decided to focus on this is because just a couple of weeks ago, there was a new entry in this saga where
And I actually add that previously just very quickly, just
Yeah.
got a nice movie there. To what extent do these mini disks themselves interact with each other?
do they interact with each
Like in
other?
this case, yeah, in this case, they're kind of fairly well separated, but do you get an exchange of material and elements in the mini disks with us?
So you do see a
Spirals
little,
on each other.
you do get a little bit of exchange between the mini disks. They do excite, if you look very closely, maybe some spiral arms. The mini disks interact in more intriguing ways if you have, say, eccentric binaries. And in that case, you can have the mini disks really strongly interacting with each other, maybe shocking against each other as they approach. Because these mini disks are basically the size of the Roche lobes for each object. And so those will be very big at apocenter for an eccentric binary potentially. But then as it gets closer, you can spew material out depending on the response time. You can have shocks between them.
Yeah.
But in this case, they are relatively well behaved. Although actually, even in this case, when people have done 3D GRMHD simulations of these, so this was a paper by Mark Avara. So they looked actually in sort of 3D sloshing motions of material between the two.
I think that's what I've seen, yeah.
Yeah, so when you don't constrain, so here I've constrained the geometry to 2D cylindrical. But in 3D, exchange of matter from one to the other can be even more extreme. And of course, it's also dependent on viscosity and all this other mess. But a couple weeks ago on Archive, this experiment was extended to even higher Mach numbers. And the point, so they approached Mach 100, so the sort of typical Shakur-Sinyaev numbers. And basically one of their main points is that if you extend this to the thinness of disks that people usually invoke for AGN, then, okay, yes, it depends on the initial condition and all that, but it could take billions of orbits or more for the disk to actually adjust to the binary. So for all intents and purposes, binary might not actually accrete that much. But then, of course, this is, as you noted, very initial condition dependent. And that's all I plan to say for circumbinary disks in general. I'm going to leave stars behind for now. But if you have questions on that stage, I can go back and just try to take care of them.
And what numbers, this approximation is like, what number is H or R to some degree?
H over R to the, or it's like R over H.
Okay. The synergy is like one of these.
Okay. Now, so going back to this lovely picture earlier, I love these old sketches before they had cameras. It was great. As we follow the journey of these merging galaxies, right? The binary dynamics are governed by a bunch of just various physical processes over the course of their journey, right? So at the early stages, the binary evolution is going to be dominated by things like dynamical friction with the dark matter halos of the galaxies. And they're especially depending on things like the size of the two galaxies, right? If you have a minor merger versus major merger. Dynamical friction can actually depend kind of sensitively on the shape of those dark matter halos or the profile. There's also, for stellar scattering, so if stars wander too close to the binary, they can carry off some energy and angular momentum from it. And of course, the efficiency of that process is sensitive to things like the triaxiality of the galactic potential and things like that. Then as the binary shrinks, those processes become less and less efficient at carrying away energy and angular momentum. And instead, the binary evolution will probably be dominated by processes like gravitational wave emission or potentially interaction with the gas disk. Although, of course, as we saw earlier, that may actually drive binaries outward rather than inward. So just another layer of complication there. But the potential presence of gas is also very exciting for trying to find evidence for these binaries at scales that are too small to be resolved in normal images. So here's just a lovely recent example of one of these dual AGN found at about a couple hundred parsec separation that is really pushing the limits of what you can resolve with ALMA here and with adaptive optics on Muse here. And that's still a couple hundred parsec separation. So as these black holes get closer and closer together, they'll just be completely beyond the reach of imaging telescopes. So then we have to get a little more creative maybe and try to look at for variability or interesting spectral features. So I will talk for a little bit on variability. So back to my favorite animation. From this system, we can pick out a couple potential sources of variability. Right, so the simplest one is the orbital period of the binary, right? So every time one of these members of the binary approaches the pericenter of this cavity, it strips off some material, and then that can briefly modulate the accretion rate onto the binary. Although that modulation depends on what the sort of residence time of gas in these miniature accretion disks is, right? So if the disks respond relatively quickly to the infall of new material, then there's more or less modulation of the accretion rate there. But beyond that, there's actually, if you look at the edge of this cavity, a very non-uniform surface density around it. And it turns out that this can actually very strongly modulate the accretion rate on not the binary's orbital period, but that of this cavity. So in this case, that period ends up being about 5 times the binary's orbital period. So we see in these accretion rate plots this envelope that corresponds to the orbital period of the cavity. And then as we go to different mass ratios, that turns into a sort of 2 orbital period variability as the cavity gets smaller at lower mass ratios. And then whether that or the binary orbital period is more prominent depends on some of the disk properties. So in this Mach 20 case, showing here, we really see a lot of this envelope, but less of the orbital period variability.
So the little wiggles of the orbital period variability, large, long period ones is the cavity.
Yes, in this case, it's easier to see. And actually, something else you can make out in an equal mass case is that because of the symmetry here, the variability is actually on half the orbital period, depending on how you look at it. So if you look at the curve for any individual one, so here the blue is the primary, the orange is the secondary accretion rate. So in some of these, you can see that they're offset by half an orbital period, right? You have this back and forth between them as one or the other approaches pericenter. Now, this is all just restricted to the simple case of a binary that is evolving secularly, very slowly, right?
Sorry, they're offset by half an orbital period, but it seems like one of them takes an extra orbital period to return back to the cycle.
This is kind of weird.
Also, yeah, also if you compare the first 2 jumps.
Yeah, I mean, they're not exactly the same. There's also this.
It looks like the orange one does one less full orbital period in that, like.
Right, so this gets a little chopped off for some reason or another, right? It's still not, right, there's still a lot more going on here than just, oh, these 2 Fourier components in a time series distribution. Actually, it pops out maybe, well, it pops out in a periodogram as well. Yeah, it's not, especially in the higher mass systems, it's not quite as clean as that. There are other things going on. You can see that maybe slopes in the Mach 20 case are a little different. And then as you go to, well, actually, depending on the Mach number, even these extreme-ish mass ratios, so 1 to 100 in the bottom row, can have some very maybe non-trivial variability, especially in thinner disks that shock a little more easily. But now what I would like to do is add more ingredients. So when the binary is widely separated, if its evolution is being driven by the disk, it can't really evolve faster than the disk, right? So if something causes the binary to shrink very rapidly, if the disk was causing it to shrink, then the disk can just, the binary won't do much until the disk viscously spreads and catches up with it. But when something like gravitational waves enters the picture, that changes. So qualitatively, the disk can respond with a typical velocity for say viscous relaxation that goes like the viscosity of the disk over a radius. And then so we'll typically have the cavity radius just proportional to the binary semi-major axis with some factor that's maybe 2 to 3 or something along those lines. On the other hand, gravitational wave emission will change the semi-major axis of the binary at a rate that's proportional to the binary semi-major axis to the -3rd at 2.5 piano order. Right, so once the semi-major axis gets small enough, this rate will become just so much faster than anything the disk can do that the binary will start just pulling away and leaving the disk behind. And of course, how this happens depends on what here I've called viscosity, but the effective stresses in the disk. How good is the disk at transporting mass and angular momentum? So here are a couple experiments where we started some binaries at 100 gravitational radii separations, and then prescribed their Inspiral according to just 2.5 pn. And in the top row, I'm showing just a relatively high viscosity disk, and in the bottom row, a relatively low viscosity disk. And in the top case, because the disk has a higher viscosity, it's able to respond faster. It actually keeps up with the binary until very, very late times. You can't really see, right? So all of these structures just scale down with the binary. So all the periodicities I showed earlier will just move to higher and higher frequencies. On the other hand, if we have a lower viscosity in the disk, and this is maybe a little more representative of the classic thin disks for typical alpha parameters. But qualitatively, if we have a lower viscosity or less efficient transport, then although the disk can keep up with the binary a bit at early times, we see the cavity shrinking a little bit from panel 1 to 3. By the time the binary reaches 20, 10 gravitational radii, it just has completely left the disk behind. And in this last panel, the density of gas around the binary is very, very tenuous, although maybe you can see there's a little gas left around it. And if you zoom in, its binary does still have little accretion disks. Turns out we can predict when this should happen very well.
So as if like the viscosity inside the zero.
Viscosity is exactly 0. Let's see. You still have a little bit of numerical viscosity in the simulations, but with just hydro, so with nothing like magnetic fields, without viscosity, matter can't really move through the disk. So eventually you just move out. So if you write down the hydro equations and don't have a dissipation term, the only steady state it can reach is just being static without motion of fluid.
Right.
So
There's gravitational.
So-
Installations gravitational potential don't like pull out some plasma from the inner edge of the disk. The plasma is with some gas in the
yeah. So there may be some sort of transient, depending on your initial conditions, right? So if you start the binary and just have a cloud of gas around it, it's going to stir up that cloud and interact with it. But if you have some disk, say initialized with some cavity, without some sort of dissipation, the disk will just stay where it is. And yeah, so it turns out you can predict roughly when the binary leaves the disk behind, actually just by comparing these two velocities. And so duh, why not? But there's also some very popular estimates people use where you compare the timescales instead and get it off by a factor of say 2 or 3 or so, which matters more when you connect the semi-major axis to a timescale you look for. So a factor of 2 or 3 in a semi-major axis gives you a pretty different timescale that you're trying to observe. But in the simulations, we can just measure the size of the cavity, so really the semi-major axis, and compare that to the semi-major axis of the binary. And then at early times, right, the evolution is pretty self-similar. And we actually see that the size of the cavity scales linearly with the size of the binary. And then at late times, they become independent of each other as the binary just zips away thanks to gravitational waves. And we can fit a break in this power law. And it turns out, so those are the dots in this figure. And this orange line is just comparing the two velocities, the spreading velocity of the cavity and the gravitational wave driven velocity or rate of change of binary semi-major axis. So this is
The semi-major axis at which you decouple
Yes.
as a function of viscosity.
indeed.
Yeah. The timescale argument is the green one.
Yes. And depending on how good you're, if I could just dream that observations are perfect and forget about all the difficulties they have, maybe you could even learn something about disk viscosity or stresses. Although first we actually have to observe these things. And if you observe it in gravitational waves, you can learn more about the binary properties of the masses, and that breaks some of the uncertainties in the scale-free arguments I've looked at so far. In terms of variability, so these panels, these messes are the full accretion rate time series for both simulations, for the high viscosity case and the low viscosity case I showed earlier. And then these inset windows are just zooming in on certain times. And all of them are about the same width, which is the default time unit is the orbital period of the binary initially, which is about 8 hours or so for a fiducial 10⁶ solar mass black hole binary. But you can, so each window is maybe 10 days or so. Apart from window C, which because the variability is so high frequency, I'd had to make that window smaller, so it's about a day for a fiducial binary. And in the high viscosity case, because the disk keeps up with the binary until very late times, just scales down and down in size, up and up in frequency, the variability just moves to higher and higher frequencies over time. You see a little bit of that in the low viscosity case, although not nearly to the same extent. And then the main difference in the low viscosity case is, right, so this orange dashed line is marking where the decoupling measurement I had earlier was. So when the binary has really started evolving independently of the disk. And later after this, the accretion rate really plummets. And in this case, over the last, say, 10 days or so for this fiducial binary, the accretion rate drops by about an order of magnitude, which hopefully would be observable. Now, for different masses, this could be months or years of this decrease in the accretion rate, which is, qualitatively similar to some things people have observed for changing state changing with AGN. But there are other potential explanations for this as well.
This is all hydro with an alpha viscosity.
This is constant kinematic viscosity, actually. So these are viscosity in natural units.
And no magnetic fields or anything.
No magnetic fields or anything.
And thermodynamics is
Yes, so in this case, thermodynamics was Mach 10. The sound speed was chosen so that h/r was 0.1 everywhere. So this is a simplified setup, but I generally trust the general magnitude of the stress in the disk bit of this picture a lot more than I trust the specific dynamics of the flow around the binary. But also, yeah, because the thermodynamics are so simplified, I just don't personally feel comfortable giving people a light curve rather than a accretion rate time series, that kind of thing. These dots are just showing that point of decoupling that we can predict and measure in the simulation for a few different fiducial Inspiral merger ring down models in the LISA band. You can probably ignore the yellow one because that's kind of low mass, but this red one is probably about the SNR sweet spot for LISA. And these dashes are 1 year, a month, an hour, or a day and an hour before merger. So depending on the effective stresses in the disk and the mass of the system, this could nicely fall within a LISA observation or one of the others.
And this is the mass of the primary.
This is the total mass of the binary.
Total mass. And what's the ratio?
This is equal mass. So if you go to more unequal masses, for a given system mass, the gravitational wave driven Inspiral will be much slower. Right? So the quadrupole moment of the binary will be much reduced. And so then this decoupling process would shift later and later in the Inspiral for unequal mass binaries. It also happened more slowly, so it might be easier to observe in that sense. And yeah, so I don't have the plot here. I've run this for lower mass systems as well, and the prediction still works out very nicely on the formula balance and velocities. And now in the last few moments, I would like to talk a little bit about binary black holes and AGN disks. So still gravitational waves, but now looking at some of the maybe more peculiar black hole binaries that LIGO has observed. And I'll give a little background, but hopefully we're all very familiar with this from Dawn's talk. So to begin with, AGN disks are good environments to produce high mass black hole mergers. So one of the challenges with producing black holes that are in the mass gap, so they're so massive that we don't think stars normally could produce them at the end of their lives. LIGO has found a few events with black holes that massive, and one event that probably has both black holes in the mass gap. And AGN disks are nice for producing those black holes because one, the deep gravitational potential well of the supermassive black hole prevents these merger products from escaping due to gravitational wave kicks. Additionally, there's a lot of gas around that can help the black holes grow. So you can have both hierarchical mergers and just the black holes growing over time from material. Additionally, presence of gas gets people very excited because of the possibility of detecting some sort of electromagnetic counterpart to these events. So people are looking for this in surveys, and there are a few candidates, although the statistical significance of that, those candidates are a little uncertain at this point, right? Just because there are so many AGN in a given LIGO error volume that the odds of one of them flaring are relatively high. But this is something that would be very interesting for multi-messenger science. As far as getting stars and black holes into the disk, there are roughly two processes. One is you can form stars in situ from gravitational instabilities in the outer edges of the disk. And this happens prolifically in standard alpha disk models that are horribly Jumara unstable. But even for these magnetically supported disks from modern simulations, there are still areas that become gravitationally unstable and form massive stars with masses, up to hundreds. And of course, these stars at the end of their lives will probably leave behind black holes, go on to give us LIGO sources. Additionally, if you have some sort of nuclear cluster with stars and black holes, and a disk forms, those stars can be brought into the disk from excitation of bending waves or dynamical friction. And this can give you a population of black holes within the disk. And then once you have a population of black holes in the disk, they can form binaries. So these are a couple studies that are just looking at how binaries form. These are both from gravity plus hydro simulations, but also gravitational wave emission from close approaches of binaries in these disks can also help them actually form bound binaries as opposed to just two black holes passing in the night. One of the interesting outcomes from these simulations is that binaries tend to form with non-zero eccentricities, so in some cases pretty high eccentricities, and oftentimes they form in retrograde configurations. So really just, this is 0 in the plot, right? So above 0 is prograde binaries, below 0 is retrograde. Although this depends a little bit on the initial conditions for the scattering experiment you run. But one of the questions that I've been interested in since I first learned about this channel for LIGO events is whether or not it's actually reasonable to say these black holes merge. Right, so even if this black hole binary forms, the initial semi-major axis for these binaries will be on the order of 10 to the 6, 10 to the 7 times the sort of horizon scale for those black holes. So they need to shrink by many, many orders of magnitude. On the other hand, if circumbinary disks cause them to outspiral, which we saw could happen for a wide range of conditions, then they could get pushed out to maybe a third, half Hill radius separation and just become dynamically unstable.
The difference from your previous setup is that now you're in a differentially rotating flow as well.
The next slide is on the setup. So to study this, we set this problem up in Athena++. So using a shearing box to capture the three-dimensional stratification of this accretion flow, the domain is long enough that we can see the development of these. This coloring, there are spiral arms here. I'll show them in a different color scale later. So we can get these spiral arms excited through the disk. I'll show these as well on the next slide, but there are little horseshoe orbit type features that we capture in the midplane flow. But we can also zoom in and resolve the flow around the binary itself with very high fidelity. And to do this, we also sort of use a hacked together custom version of Athena++ that couples it to the rebound n-body integrator. And we found actually after some initial studies that using some sort of approximate orbital evolution for the binary just did not cut it at all. So we were originally solving Hill's equations, and those were okay for circular binaries, but when we tried to do eccentric or inclined ones, we found that they gave us pretty wrong results. They also, those cycles were very wrong. The other thing is we implement something called torque-free sinks, and this was actually also applied to the normal sort of isolated circumbinary disks earlier, but some studies will use a sink prescription that ends up applying a, say, 3 to 6 or something order of magnitude too large accretion torque from the removal of gas on the disk. And that can give you very incorrect flow structures and give you very different values for things like relative accretion rates, disk structure, things like that. But anyway, so we use a sync prescription that doesn't exert an unphysically large spin torque on the disk. And this is what we get. So here's just a zoom in of one of these mid-plane flows. You can see these horseshoe orbits traveling through the disk. On larger scales, it's very similar to sort of simulations of planets and disks, but then, right, so once the flow enters the Hill radius of the binary, then we get this accretion disk forming around it. Each of the members of the binary gets its own accretion disk. It's all very nice. On large scales, we have a meridional circulation pattern developing. So most of the accretion onto the binary actually happens in the vertical direction. And this actually is very similar to, I don't have a picture here, but for just a Jupiter mass planet in a disk, the same sort of flow patterns
What are we
develop.
seeing on the right hand side?
So the right-hand side is a slice. So the radial direction is along the horizontal direction and Z is vertical.
We're still just looking at the shearing box from the side now.
Yeah, so this is just looking at a slice through the side.
And John shearing, yeah.
This is makes sense, right? Because it's not supported by the angular momentum.
Yeah, yeah. So the accretion, right? So further away from the binary, you have pressure gradients in the disk that can support it vertically. But as you approach the binary, the vertical gravitational field is very different from that of just the normal AGN disk. So a lot of material falls in from the top, and then you have this circulation of material coming in from the top and then actually out through the midplane. And so this three-dimensionality makes it, well, there's a lot more freedom in how the energetics of the gas can change. And this three-dimensionality ends up affecting the orbital evolution quite a bit. So I don't have the comparison here, but if you compare just simple circular prograde binary 3D versus 2D, the typical inspiral rate is much, much faster in 3D than in 2D. Sort of the power law is like -1 versus -3.
Even if you start everything as coplanar to begin with. You're not starting the binary inclined.
Yes. So this study that Adam Dempsey led was looking only at coplanar binaries and prograde configurations. And here actually their study was looking at basically different disk scale heights. So really the dimensionless parameter that matters there is the difference between the Hill radius and the disk scale height.
So even in the coplanar case, you drive much more efficient mergers if you have 3D rather than 2D.
Yeah, and basically you get something that looks like, let's see, like this is just a dot, and here's 0. And then, so if this is like binary semi-major axis normalized by Hill radius, you find something like this is for 2D, and then 3D looks something like this. I mean, so it's much lower than the 2D. And then as you get to very small separations, there's uncertainty over whether or not the simulations were actually able to resolve the flows in this study. But certainly the difference is, I don't know, maybe a factor of 2 or something between 2D or 3D. So Adam's plot on paper has that plot very nicely, comparing for a bunch of different disk properties or binary properties, 2D versus 3D. If we zoom in on the binaries themselves, we can see just these accretion disks around each. So in the prograde case, the mini disks look pretty similar to the isolated binaries, but in the retrograde case, the binaries experience a pretty severe headwind and get stripped of most of their material. Actually, so we can see here, right, so when matter enters the Hill sphere, it has some handedness, and for a prograde binary orbit goes along with the flow of gas within the Hill sphere. But in a retrograde binary, it plows into that and feels a headwind. So we can see these mini disks get very reduced in size, although they still form nearest to the binary. You can see these sort of trailing streams of material behind it. Or we can try to see, it depends on which screen you look at. So this is zooming in. What are these units? So each tick, so the big ticks here are half of a binary semi-major axis. Right, so these are, this is in the binary, the frame of the binary's orbital plane. Yeah, so the big ticks are half the binary semi-major axis, and then the small ticks are a quarter. So this is now zooming in right around the binary. These are surface densities actually, so these are density projections along the binary angular momentum vector. But when we look at orbital evolution, in the main difference, so these are just looking at different inclinations of the binary orbit. The overall is the blue stars. Also, we broke it up into gravity and accretion contributions. And so for the prograde binaries over here, retrograde over here, the retrograde binaries end up inspiraling much, much faster than the prograde ones. So instead of this power law being -2 or -3, and this is just a dot as a function of m dot, so rate of change of binary semi major axis again in units of accretion timescale. But then the retrograde binaries end up inspiraling much, much faster. So instead of semi major axis changing by, so the mass of the binary changes by a factor of 2, and for the retrograde case, the semi major axis could change by a factor of 6 or 7, or 2 to the 6 or 7. That sort of thing. There are some hints, so all of these binaries I showed were near circular, but because of three-body interactions, they do have non-zero eccentricity excited in them, and so the prograde binaries seem to be stable to these eccentric perturbations. So any sort of eccentricities in the binary system get damped by interaction with the gas, but then retrograde binaries have some hint that they might actually be unstable, that interactions with the gas might grow their eccentricities over time. And for all of the binaries that were out of plane, they experience this inclination damping, so they get pushed towards prograde alignment with the disk midplane. And of course, if you start with a retrograde binary, this brings them through the quasi unstable region at high inclinations. So that can be potentially interesting as well.
Now, the eccentricities that you're exciting are only like 0.05, so you don't necessarily need to have an inclination above 40 degrees for cosi to do that.
Yes.
It's the Lagrange dynamics, or whatever you want to call it.
Yeah. Although here actually, so because these binaries are, we are looking at ones with separations on the order of maybe a quarter of the Hill radius. It is a little trickier to find out which range is quasi unstable and how high eccentricities they reach, because none of the doubly averaged stuff definitely doesn't. But yeah. In a follow-up, we looked at binaries. So this was led by Josh Calcino, who's now at Tsinghua. And this was just looking at sort of aligned or anti-aligned binaries, but at different eccentricities. And here I'm only showing the retrograde ones. And as we go to higher and higher eccentricities, the rate of eccentricity pumping gets higher and higher. And so we can understand this physically fairly easily, actually. So the binaries experience a drag force as they're plowing through this disk, experiencing this headwind. And at apocenter, right, so we have an eccentric binary. So the lever arm at apocenter is very large, and the velocity is very low. So this drag force gives you a very strong torque and not much power. So the angular momentum of the binary is sapped away, and its energy isn't changed much. And that ends up pumping the eccentricity. Now, the counter to this is if you have some interaction in the pericenter, of course, that could damp your eccentricity. But because these binaries don't have substantial mini disks to speak of, the interactions near pericenter are not very strong. And so we looked at this a little more quantitatively by breaking up the contribution to the rate of change of the eccentricity as a function of orbital phase. So we just folded it on binary orbital phase. And then after symmetrizing that, so looking at the offset from apocenter, we see that most of this eccentricity pumping is happening right around the vicinity of apocenter. And then the stuff away from apocenter sort of washes out. And with that, I'd be happy to take some more questions. Thank you very much.
Thank you very much, Alex. We do have about 5 minutes for questions. So just keep your hand up. I will take question.
So Shang-Chi Huang used to be here. Officially, I'm on the paper, although I didn't do very much. He discovered these wide spin binaries are extremely eccentric. This means above sort of 10 to the 3 AU and mass ratios of 0.95 within 5% of being equal masses are ridiculously eccentric. They're not just super thermal, they're like hyper thermal. Everything is super eccentric. The subtitle to this paper was Evidence for a Circumbinary Disk Origin. Now, I objected to that, but as fourth author, I was over. So the idea being that you need these very, very wide binaries to somehow know about each other. Like there has to be some special property due to the fact that they have equal masses. So first of all, they have to equalize their masses. And then they have to maybe be kicked by some flyby, kicked into a hugely eccentric orbit. So it's 2 tooth fairies required. Could you comment on either of those two fairies?
As far as the eccentricities, at least, so I haven't done too much on this yet, but the problem has been looked at a lot for the Mach 10 case. People have simulated that one to death now. And in that case, you get sort of a, well, we don't know. Some results find that you get, if we have E dot, so here's 0. So some people find that you get something that's like a negative E dot over some region, and then something like this. So this is maybe 4 or so.
The function of.
As a function of. So some people, so there may be a few different stable equilibria. So maybe eccentricities get damped to 0. Maybe they get pumped if they're below, 0.4, 0.45.
We discussed this some time ago at the Astrophysics.
Yeah, and this is also related to the gravitational.
This is not going to give me the 0.95
Right.
electricity, but it may equalize the mass. So do you think equalizing masses for one thing is a sensible outcome of Circumbinary disk evolution?
Equalizing masses seems sensible. Yeah, so this is the Mach 10 case. There are some hints of looking at this indirectly through things like the mass of a self-gravitating disk that suggest that this equilibrium eccentricity can shift around a bit depending on disk properties, but that hasn't been systematically explored. There's also questions whether this is stable or not. Some people find that even 0 is unstable.
So equal mass is a kind of attractor.
Equal mass does seem to be an attractor, yes. At least for thinner disks, right? If we have puffy enough disks, if they're thick enough, then the attractor may break down or be much less.
Do you think it would remain an attractor if you put it into some realistic formation scenario where there's a lot more?
Yeah, I don't know. I don't know how sensitive this is to the interactions.
I've got a question regards what you were talking about at the end there with well, these kind of embedded binaries. So you talk about these different channels capture via the nuclear star cluster, where you expect sort of kind of random orientation perhaps of capture there versus formation in situ, and then sort of maybe coming in and getting captured in the disk, which would maybe favor prograde kind of orientations. Is that right? Slightly.
I think that relates a little more closely to the sort of inclinations we might expect, because formation in situ should probably have formations at most on the order of, say, the scale height or something, at least before you can also technically some higher inclinations. But then if it's coming in from a nuclear star cluster, it might have initially a very high inclination relative to the scale height of the disk. So that as far as I don't have the plot. Don's group, one of his current students, also Variability, looked at binary formations, so just scattering experiments basically. And it seems like prograde versus retrograde depends sensitively on things like how quickly objects migrate through the disk or the initial separation. So if you start them at 2 versus 3 mutual Hill radii, that sort of thing ends up affecting whether if they form prograde or retrograde binaries.
Okay. Yeah. Because I guess, if there's some sort of imprint on their final of the eccentricities and then any sort of multi-messenger signals from that, where that tells us about the channels that they're coming from.
Yeah, there might be some hope with things like the spin chi effective mass ratio correlation, things like that, but for mass ratios or eccentricities. But
any other questions in the room? I'd like to give you the floor. You had, I think, one more slide that you could share with us, given the fact that we've got your sound working. So let's
try this. So I thought a little bit about eccentric binaries. And here, actually, so there's another interesting thing that I glossed over. And that's that we have this eccentric cavity around the binary. We have a binary. So just from gravitational forces alone, that binary has a quadrupole moment. So this eccentric disk should precess due to that quadrupole potential, right? It's non-Newtonian. And also there are pressure effects and other things that cause precession. And with a circular binary, that doesn't change things too much. But when you have an eccentric binary, there's another preferred direction to the system because of the eccentricity of the binary as well as the eccentricity of the disk. So then the relative precession between these can cause some interesting behaviors. So let's see if this works. So here, these are snapshots taken so precession is a much longer timescale phenomenon. It happens on maybe hundreds of orbital periods. So here I'm just showing a snapshot of surface density every orbit that has been time averaged in a seasonally appropriate way or made into a time series. if the audio is working, which it doesn't seem to be.
Ah, disappointing.
So I can make my computer make noise.
Yeah, let's do that.
Oh, no, you know why? I didn't share properly. I need to share and share audio as well.
Yeah.
Oh, no, it was clicked. Okay. I can't believe it. But the scientific thing is that it's right, but you can see the accretion disk, the mini disk being more prominent around one and then the other. This comes down to the relative orientation of the disk and the
What's the binaries axis? Like, what's the
yeah, so
direction?
the binary axis is something like this. And then so this binary is going around like that. And
Okay.
yeah. And then so here at one point the disk is oriented like this, then the other. Yeah. Yeah. So depending on the relative orientation, you can have more accretion onto one. And it washes out in the end, but even there's some fun stuff here.
Great, so with that, I would just announce that we've still got, I think, a few dinner slots available, so please sign on before I book up later today. Otherwise, let's proceed to lunch and thank Alex once again for a really illuminating talk.